So, good afternoon, everybody. You guys at home cannot see me, but it's me and 6 other students in the classroom. So it's not empty as you see there on the screen. And today we will continue on chapter 1, an introduction to demography. And we reached up to the part about the different sub-areas in demography that I've been calling here them demographic models. And so I discussed a little bit more in detail what is formal demography. And formal demography, it's pretty much when the whole study that you are doing and that takes into account some sort of demographic changes or demographic variables, both the dependent and the independent variables are demographic. So because of that, to better understand what independent variables and demographic variables are, that's the reason that at the beginning of this lecture, I added those slides about what variables are, what observations are. But here in formal demography, it's kind of like we would say the traditional demographic studies. It's when researchers, they were focusing or they had a main interest on how some demographic variables affect other demographic variables. And just to let you know, I cannot see the chat here on my screen. I just tried it. So if you want to say something, please just unmute yourself, okay? And say something. I think I can hear someone. You should just unmute yourself because I can just hear some noise from someone who I don't think is trying to talk anything. I guess the person just organized it because everybody's on mute now. But feel free to unmute yourself and say something if you want, ask questions and so on. And then the second group of demographic studies that I talked before is when we are trying to understand associations between non-demographic variables and demographic variables. And these studies in general, we call it social demography because it's pretty much we are trying to understand the associations of changes in fertility, changes in mortality, and changes in migration with other variables from other sciences within social science. And in this subgroup here, that's being called Population Studies 1, it's pretty much when we have a non-demographic variable as the independent variable or the main independent variable, the variable that will explain changes in our dependent variable, which is demographic. And some examples of non-demographic variables here, we have, for example, social class. Social class, it's a concept in sociology that can be measured in several ways. It can be measured based on income, it can be measured based on occupation, it can be measured based on wealth of individuals, how many properties people have. And social class and social economic status, they have an association, a correlation with death rates, in the sense that people with higher social classes, they have lower death rates. And all the time here, when I'm talking about these associations between variables, I'm being careful. I'm using the terms association and correlation. I'm not using the term relationship. I'm not using the term causality. Because I talked to you before in this class that sometimes one variable causes variations in the other one, and the second one also causes variation in the first one. When you have one variable making changes in the second one, and then the second goes back and makes changes in the first one, you have reverse causality. When you have reverse causality, your analysis is more related to association, to correlation, right? So just a matter of being careful with those terms. And social psychology, for example, attitude about motherhood, whether a specific group of women from specific characteristics, they would like to have children, that will impact the number of children that they will have. Number of children is fertility. And the annual rainfall rate of a specific area, so a geographical variable, that might affect population density. Some areas that might have more annual rainfall, it's really hard to live there, and then you're going to have less people living in that area. Or the opposite, some areas that don't have any rain at all, they become just deserts, and it's hard to live in those areas. That will also decrease population density. It's just to show, and some areas that have really high population density, and then we have a lot of emissions, CO2 emissions, that can affect the environment, and that can affect geographic variables as well. So this is an example that I just showed you now of reverse causality. Economic opportunity, jobs available. If I have a country or a state with a lot of jobs available for people, people will tend to migrate to those areas. So high economic opportunity increases in migration. Here I'm using the term for internal migration, or immigration, using the term for international migration. But also when you have more people entering a specific area and they are going to be looking for more jobs, then you start to have less availability of jobs. But at the same time, when you have a lot of immigrants coming to a specific area, they will also demand more products to be produced in that region, that area. So that might also create jobs as well. So that's a really complicated relationship. And it's a really controversial relationship between economic outcomes and migration, as we're going to talk throughout this whole semester, mostly on the chapters about migration. Because some people say that immigrants, they just hurt the job opportunities of US-born workers, and others say, no, but immigrants, they also demand products, and then that generates more jobs in that specific area that receives a lot of immigrants, right? So, but in this population studies 1, the idea is that we are focusing on a non-demographic independent variable, or the main variable they are trying to use as the explanation is non-demographic, and the consequence is demographic. And population studies 2 is the opposite, when my independent variable is demographic and the dependent variable is non-demographic. For example, if a specific region has a higher proportion of young people in general tend to be more liberal. And then they have that area, we have a specific voting behavior. If a specific county has more higher proportion of older people tend to be more right-wing, and that will be associated with voting behavior. If you have more migrants in a specific area in younger ages that don't have job opportunities, they will start to put pressure in the government to create changes to the population, and then that might create social change, which is a concept in sociology. So I guess now you might be able to see me on the screen there. I think it's good enough for now, right? You can see me here. And another example, birth rate. Birth rate being a fertility variable. And if we have a high birth rate in a specific country, that will increase the proportion of children in that specific country. So we're going to need more services for infant and children, including health services, but also schools and so on, health, childcare, and all these different services that we'll need for the a higher proportion of children in that population. My dissertation is pretty much, I'm looking at how people getting better educated and older, people getting older, why people getting older? Because now you have a decline in fertility, people having less children, and also people living longer. So you have higher proportion of people in older ages. And in my dissertation, I did the work for Brazil. So people are getting older, but it's still not so old anymore proportionally. So you have a higher proportion of the population between 15 and 64 years of age, which is exactly labor ages. And people are also tending to have better education, not as good education proportion as in the US, but you have a higher proportion of people finishing high school and entering college as well. So my main idea was like how declining fertility, declining mortality, making more people being between 15 and 64 compared to previous decades, and also changes in education, people getting better educated, how that affects the earnings of the population. In my case, it's a non-demographic variable. Earnings is an economic variable. And the idea is that older people have more experience in the labor market. They have better education, so they make more earnings. So there is a positive association there. But since now you have more people, more better educated people, and more older people in the labor market, you would also see some competition for work, and then earnings of these people would go down. But what we see in Brazil is that there is a huge demand for better educated people. So although the proportion of people in older ages and with higher education is increasing, you do need that kind of people with more specialty in the labor market. So although you have a higher proportion of them, their earnings is not decreasing. How did I come up with this idea? The dissertation is pretty much an application to Brazil about something that was already done in the US. In the US, with the baby boom cohort, right after World War II, the fertility rates increased a lot in the US, right? And then the people who were born right after World War II, they entered the labor market at the end of the 60s and beginning of the 70s in the US, and they have also higher education compared to previous cohorts. So they enter in bigger numbers into the labor market, better educated, but they were competing with each other, and that had a negative effect on their earnings. In the case of the US, had a really clear negative effect. In the case of Brazil, it's still because we don't have such a high percent of the population with college education, still we didn't see that a strong negative effect on their earnings. But so pretty much my analysis in Brazil was the same thing that was done here in the US since the 80s based on data from the 60s and 70s, okay? But this is just to show that really important analysis that we have in demography, not necessarily we are just looking at demographic variables. We are looking at associations between demographic variables and non-demographic variables, okay? So I just mentioned now cohorts, the cohort born after World War II. So just to make it clear, cohort is a group of people who have experienced a common event during a given time interval. Usually in demography, when we talk about cohort, usually we are talking about birth cohorts. So people born around the same years or the same decade. So they are also called as generations. And this professor from Florida State University, he mentions, why do we care about cohorts? Why do we study cohorts, or birth cohorts more specifically? If you understand what distinctive opportunities and problems were faced by specific people that were born around the same time, we can try to better understand what are the challenges, social, economic, and demographic challenges being experienced by those generations. And that can be used to better implement policies for future generations as well. I just mentioned the example of my dissertation doing the analysis of Brazil, and I pretty much used studies about cohorts in the US and did similar studies for Brazil. So if we understand these dynamics in other countries, we can explain another country, but also if we understand a specific generation in one country, we can better understand what we should expect in future generations in that same country. And cohort here at Texas A&M, you always see, I mean, people who just started here at Texas A&M last year, you might have seen at the bookstore on MSC, those shirts for sale, class of 2024, right? So it's pretty much the cohort of people, of students that started at A&M in 2020 are expected to graduate in 2024. In that case, we are not talking about birth cohorts, but we are talking about people entering, experiencing at the same time the college, the university system, right? And yeah, so that's one example of cohort as well. That's not related to birth cohort. And here, there are some examples of cohorts. So people born during the same period who experience similar social circumstances throughout their lives. These terms are not always used in the same ways by different researchers, by different demographers or social scientists. And those years, they might vary a little bit from study to study. But I put here information based on the textbook, and I added some more the new cohorts that were born in more recent years. So the lucky few were those people born between around 1929 and 1945. So at the time of the Great Depression, that's when they were being born until the end of World War II. And at that time, because of these economic issues that the US was experiencing in terms of the Great Depression, and then World War II was going on, people started to have fewer children. So by having fewer children, these people here who were born among these years, later when they became adults, they have less people competing for resources in society. So they have more resources for education per capita, per student. And also they have more job opportunities because there were fewer people competing for these resources. The baby boomers is exactly when you experience an increase in fertility in the US and also in other countries, right after the end of World War II until around 1964. And then after that, you start to see a decline in fertility. So you had this moment right after World War II, more economic opportunities, people really happy with changes in society, having more children. But then after a while, fertility starts to decline. And between the mid-1960s and early 1980s, you have what's called the baby bust cohort that some people also call Generation X. And the millennials, also called by others by new boomers or Generation Y, are those born from early 1980s to early 2000s. I guess most of you guys here are actually Generation Z, who were born starting in the 2000s. And, but maybe some millennials as well. One student I was talking to him earlier today, and I'm not going to say his age, but I guess it's before the 2000s. And in my case, for example, it's funny because I'm 1977, and some researchers put me in the group of the baby bust cohort, and some others put me in the group of millennials. But what's important to understand here in terms of the cohorts is that we are putting together people that have really different experiences in their lives. Getting someone who was born, like in my case, in the late 70s or in the early 80s, and comparing with the experience of people born in 2000 is completely different. All the technological advances that we had at the end of the 90s and beginning of the 2000s, and also health advances, everything. The life of the children who were born, who were raised in 1980s is completely different than the 2000s. But that's just a way to summarize a little bit these generations, to aggregate them. But of course, if you want to go in depth into this analysis, we should subdivide these cohorts. But just to keep giving an idea, this is exactly what I said before. They were fewer compared to much larger numbers of people in the following cohort, which was the baby boom cohort that were born between 46 and 64. And the smaller size of the lucky few had enabled them to have higher employment rates because fewer people were competing for jobs. And they have more social opportunities than members of previous cohorts and also of following cohorts such as the baby boomers. And Dudley Poston, the author of our textbook, he just wrote this short article, and he put this table there for all these different cohorts: the New Worlders, Hard Timers, Good Warriors. The Good Warriors are also called the Greatest Generation because they were born right around the Great Depression, the 1930s, and they were the ones who fought World War II. So that's the Good Warriors are the greatest generation that we usually hear that term. The lucky few, baby boomers, Generation X, Millennials, and Generation Z that we mentioned before. And here, just to give an idea of the range of years when they were born, the age range that they are right now in 2020, we are already in 2021. The number of them that were born in total. So you see the baby boomers, because of the increase in fertility, the lucky few in total, 44 million were born. And then baby boomers increased to almost 76 million here in the US. And this is the amount of them alive up to 2019. And this is pretty much the number born per year, which again show that the baby boomers increased a lot the number of people born. And once you have more people being born in the baby boom cohort, that has an effect on future generations, because now you have more women and men in absolute terms that will give birth to, that will have children in the upcoming generations. Okay. Yep.
How are there more alive in 2019 than born total in those like Generation X, Millennials? That numbers are higher and alive than born. That just
wow.
How does that happen?
That's a good question. I should check the article here again. No, because like,
Sorry,
that's good because this data is from 2019. They should not be born anymore.
Maybe because of the overlap. I don't know.
Good question. We'll check it out. I mean, these three last rows here, these 6 cells have this one, even this one here, number born in total and alive in 2019. Is that because of mortality? People? No, that should include it. Because those ones are people who were.
I wonder if they just switched the numbers.
Maybe they just switched this, or maybe I did it by mistake when I copied the table because I did it by hand. This was a figure from this website. But thanks for catching that. So the question was about these 3 rows here, the 6 cells that maybe those cells are switched from number of people born in total and they're alive here. Thanks, so we check it out. And here it's a graph that it's available in the textbook. And just to show the number of people from each one of the cohorts per year in millions. And then you see that from Good Warriors to the lucky few, there were not such a huge increase in the size of the population. But then when you get into the baby boomers, you had this huge increase in the overall size of the population. But then, because you have a huge increase in the size of the population, these people here are going to have children that will be born in future generations. So it doesn't go down anymore because now you have more people available to have children, right? And also, this is another graph to show how the population was kind of increasing the number of people being born over the years, because on average, women were having more than 2 children in their reproductive lives. But then you have this jump in the baby boomer cohort that increased a lot the size of the population. And then because of now having this bigger population, you still have bigger cohorts coming afterwards, right? But fertility now is lower, but you still have this stock of people that can have children. And this diagram here, the Lexus diagram, it's not included in the textbook. So that's an additional topic that I included here in our lecture. It's just because the Lexus diagram, it's a simple graph, a simple diagram that we can understand how the cohort sizes, they vary per year. So it's pretty much a graph that we have time in the horizontal axis and age in the vertical axis. And the Lexus diagram, you can show it as having one lifeline, one line in this graph for each person that we count in that population. And each person will start on time TB, where TB is the person's birth date and 0 is the person's age at birth. So each person will start in the Lexus diagram if you're taking into account only birth. If you're not taking into account migration, they will start at the time T in the horizontal axis. That's the time in which the person was born, and the age of that person was 0. So the person is touching the horizontal axis. And then the line goes up to the right with a slope equals to 1. And so people age 1 year in 1 calendar year, and the life goes up until time and age of the person's death. So this is pretty much the Lexus diagram, just showing exactly what I explained before. You have the horizontal axis here for time, the vertical axis for age. This person here was born around 1910, and then this person got older 1 year for each calendar year, and this person died around 1990 at around the age of 80, right? We can also have the Lexus diagram taking into account migration. If we take into account migration, both in migration and immigration, so people can enter a specific country in already older. So let's say that someone entered this specific, let's say that this is a Lexus diagram for a specific country. And someone entered this country at the age of 20 in 1980. So the lifeline of this person would start right here, 1980, 20 years old. So it starts from here and would go up. And if we are also considering immigration, let's say that this person left this country, arrived there in 1980 with 20 years old, and then left 20 years later when that person was 40 years old. So the lifeline would just go from here, 1980, 20 years old, until 2000, 40 years old, right? But in this specific example here, that I took it from another textbook, and this textbook, the reference, you can see at the end of these slides, you can download it for free, the PDF of the entire textbook from the Tamu library. And this is more a technical textbook. It's pretty much related to more demographic techniques. And the exact techniques that we use in demography behind the scene, it's another course that we have here at Texas A&M, Sociology 320, Demographic Methods, which would be the second demography course that we would have here, and it would be more technical. And then I discuss more in detail the Lexus diagram. But what is interesting about this Lexus diagram? How many people between 1900 and we expect up to 2200 will have reached the age of 20 based on data from this graph here? Can we answer that question with the Lexus diagram? So from 1900 to 2200, how many people reached age 20? So I just draw a horizontal line here on age 20 and count how many lifelines cross there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This person here did not reach age 20. So here I asked you how many people reached a specific age. So I draw a horizontal line in the Lexus diagram. And if I ask you here how many people reached, what's the size of the population, of this population here, considering that we just have these people, in 2000? What's the size of population in 2000? In this case, we're going to draw a line from 2000. It's going to be a vertical line, and then we're going to have two lifelines crossing it. So the population in this specific area here in 2000 has only 2 people. Okay? How many people reach the age of 60? You draw a horizontal line here, crossing on age 60, you have 5 people. How many people were alive in 1980? In this case here, 3 people. Consider that this person here did not reach 1980. Okay? So just to show that with a really simple graph, we can already see the size of the population in a specific time and how many people reach a specific age. And this is kind of like, if you think, this is exactly what a cohort is. People born around the same time and going up through time and reaching a specific age. You could even think here these lifelines may be as a group of people that were born at the same time and died also at the same time. And as I'm going to talk to you guys here throughout this semester, usually when we have a survey, we have, for example, a questionnaire, that we have a bunch of questions and we want to know more information about a specific population. I don't have money to get an interview from everybody. I get a sample of this population, few people that are representative to this population. That information, it's going to be about a specific year. In a specific year, I'm implementing a questionnaire to get information about a specific population. When I'm getting information about a specific year, I have period data, getting data for a specific year, representative for a specific year. If I get data from a group of people back here in the 1910, and then 20 years later, I get information from those same people that answered my questionnaire in 1910. And then afterwards, when they are 40, I go to the same people who were born back in 1910, and I ask them questions again. In that case, my data is what's called longitudinal, because I'm following the same people over time, and I'm looking at the variations of their socioeconomic status, their educational variables, and so on. So that's a different approach that I can do in terms of data collection. I'm following the same people over time. But follow the same people over time is too expensive. It's hard to find people over time. Maybe they moved, maybe they refused to give the interview a second time that I stopped by their household. So what a lot of demographers do, they get period data. For example, I had a survey that was representative for 1920. I got another survey with different people, but it was representative for that country in 1940. And then in 1960. So I have 3 different surveys with 3 different groups of people, but they were representative for the population 1920, 40, and 60. So I can put together this data and compare people in 1920 that were 20 years old, 1940 that were 40 years old, 1960 that were 60 years old. Not necessarily the same people are answering my question over time, but I can do an analysis of changes of these major cohorts using period data. So I'm using period data for each one of these 3 years, but since they are representative for these 3 years, 1920, 1940, 1960, I can put them together and say that this group of people who answered my questionnaire back in 1920 is representative to this cohort back here, and then in 1940, and then in 1960. So just to show you that this, you have first period data and then longitudinal data, which would actually follow the same cohort, the same people over time. That's really expensive to do. So a lot of times we put a bunch of period data together. The period data, it's also called, that's another technical term that you might hear, cross-sectional data. And why it's called cross-sectional data? Because in a specific period, if you interview a series of people to be representative of the population that specific year, you are crossing a series of different sections. You are crossing a series of different cohorts, right? So whenever you're talking about, oh, I have cross-sectional data, that's because you're analyzing data for a specific year. You're not following the same people over time, okay? And this slide, I'm pretty much showing you, explaining what I just did while I was showing the graph. To find the population size, you draw a vertical line upward from the time point, and then you count how many lifelines cross the vertical line. That was my question of the size of population in 2000. And then to find how many people survive to some age, draw a horizontal line across at the height corresponding to the age that you want, and count how many lifelines cross that horizontal line. And that was my first example of people that reached age 20, right? And I also said, in that example there, we are not considering migration. We're just talking about people entering through birth and leaving through death. But we can also consider immigration. Immigrants to a specific country, to a specific area, their lifeline start at the age and time of immigration. And immigrants, they leave at the time that they leave that specific area. So, like I just said, you can see the cohorts in the Lexus diagram is the group of people sharing the same birth date, group of individuals followed simultaneously through time and age. Their lifelines run diagonally up the Lexus diagram all together. In a cohort, time and age goes up together. For each calendar year, we have one more year of age for each individual. The idea is that cohort shares the same experience. That's why it's good to understand the experience of these people all together. And this is just another way to show the Lexus diagram using those terms that I told you before. If you have data collected for each one of the years, for a specific year, you have data for a specific period, and the idea is that that data is going to be representative to that population in that specific year. You can also collect data over time for people in a specific age. So you can see changes in how people think and how people behave and how people in level of earnings and level of education and so on for people in a specific age group through time. Or you can follow the same people over time. to do analysis of cohort. If you follow the same people that answered your questionnaire back here, and they answer your questionnaire here, and they here, and so on, that's again longitudinal data, also called panel data, right? P-A-N-E-L, longitudinal data or panel data. That's too expensive. It's really hard to get longitudinal data. You can get a lot of period data from different years, put them together, and then have this, get pretty much these people that cross this cohort from period data to see how they changed over time. But not necessarily when I put all this period data together, it will be the same people being interviewed. But with the assumption that the period data is representative to the population in a specific year, I can put this data together and create this imaginary cohort of people putting together a bunch of data from different periods. And when we calculate a period measure, when we have, for example, data about how many children women had, and I collected that data, let's say, only for 1980. So I just went to 1980, and I collected data for women, and I asked them how many children they have right now. And I asked that information for women in different age groups. Usually that information is asked for women between 15 and 49 years of age. Right? So I just went in 1 year and asked that question to women. You can ask that question for younger women and older women as well. So you went to a specific year, collect information about fertility for women. So we are using a period measure because we have this data for that specific year. If I calculate, for example, for each one of the age groups, women between 15 and 19, how many children they had throughout their lives up to that year of 1980. And how many people between 15 and 19 are in 1980. So I get the number of children that they had and divide by the number of women in that age group. Do the same thing for a woman between 20 and 24. How many children they had up to that year of 1980, and how many women between 20 and 24 are in that year. So what I'm calculating are fertility rates for specific age groups. Calculating fertility rates for specific age groups. And then if I add up all these rates across these age groups and multiply by 5, because I'm doing this age group every 5 years, I have the average number of children that women are having. So if I get for a country, for example, the final result of this calculation, I get women, how many children they had in a specific year, only women between 15 and 19, 20, 24, 25, 29, until women 44 to 49. And divide each one of these numbers by the number of women in those age groups. Add them all, multiply by 5. That's what in demography we're going to see more in detail in the upcoming lectures, the total fertility rate. And the total fertility rate, what is that? It's the average number of children that women are having in that specific country, in that specific year. But it is a hypothetical rate. This data is an imaginary, we are creating an imaginary cohort whose life experience is pieced together from the experience of different people found at different ages in one single period. Let's try to understand. I got women from 15 to 45 years of age. For each 5-year age group, I ask how many children they are having, and I know how many women are in that age group. Calculated this age-specific fertility rates. Add them all, multiply by 5. I get 1.76. So women on average are having 1.76 children. But women who are now 15 to 19 and report a specific number of children, when they become older and they reach the group 20 to 24, the chances of having children 5 years from now for that age group will have changed. It's not going to be the same. So what I did here, I got information from a specific year for all my population, and I'm saying, if hypothetically I got a group of women that were 15 years of age and exposed them to all these age-specific fertility rates throughout their lives, they would have on average 1.76 children. So I'm getting a period measure and actually doing the analysis as a cohort measure. So this is important to understand because I'm pretty much saying that I get a measure for 1 year, and I'm saying women overall, they're having 1.76 children on average. But again, going back to the example, women who are now, they report a specific rate, age-specific fertility rate between 15 and 19 years of age, when they reach 2024, 5 years from now, the rate is going to be different. It's not going to be the same as women who are 2024 now. 10 years from now, when they reach 25 to 29, the chances of having children is going to be different than when women were 25, 29, 10 years ago, right? So the experience of each group of women is going to differ as they get older. So to better understand that cohort, I had to capture the data longitudinally through time. But I'm capturing 1 year. So I'm getting period data and analyzing it as cohort data. Let's suppose that we have this group of women who experience these fertility rates from 15 to 49. They would have 1.76 children on average. Right? So that's an important thing to understand when we are getting period data and getting these measures, trying to say how many people on average would be born from these women. The same thing for mortality. How many people died in a specific age group in a specific year, and how many people were in that specific age group at the beginning of the period. Those are mortality rates for specific age groups. If I get that data for one specific year, and I get the result of 82, I'm saying that people are on average living 82 years. But how exactly that data was collected? I got data for one specific period. And I'm saying, pretend that this data is for a cohort. If I get people and expose them to these mortality rates throughout their lives, they will live on average 82 years of age. Question? For example, someone who is 30 to 34 years of age now has a chance of dying. And that person will report here to me that chance of dying. Those groups, I know how many people die in that age, 30 to 34, and how many were alive at the beginning of the period. 35 to 39, 40 to 44, and so on. But the people who are now 30 to 34, 5 years from now, when they're 35 to 39, their chances of dying, now that they're 35 to 39, is lower than people who were 35 to 39 5 years ago. Right? Does it make sense? Because we are improving the mortality rates. Health is improving overall. We have technological advances, better health systems, and so on. So someone who is 30 to 34 now, when that person becomes 35 to 39, that rate of dying here is going to be lower than someone who was 35 to 39. But we are getting information for people from different ages in a specific period and say, on average, people would live 82 years. That's because they're saying, if we expose a hypothetical group of people to those mortality rates, they would live on average 82 years of age. This might sound complicated to understand these hypothetical cohorts, but it's an important way to understand later on each one of the measures that we're going to calculate, such as the total fertility rate and the life expectancy at birth that were my examples here now, okay? And so pretty much what we are doing is this. We are getting data for a specific year and interpreting it as it is data collected for a specific cohort, right? I'm getting data for people with different ages in a specific year, and I'm saying, if a group of people were exposed to these chances of having children, first example, or these chances of dying, second example, throughout their lives, they would have on average 176 children, and they would live on average 82 years, in my example, right? So I'm getting period data and saying, interpret it in a cohort manner. We call this imaginary cohort. We call this imaginary cohort the synthetic cohort because we are piecing together data from a period population. Age-specific cohort rates of the synthetic cohort are the age-specific period rates of the period population. And this concept of synthetic cohort is central to demography because we are actually getting data for one single specific year and say, if a group of people experience these rates here throughout their lives, as they get older, they would have this amount of children and they would live this amount of years on average. Okay? Cool. And now another topic within this chapter 1 that's also beyond what is in the textbook is for us to, it's good now, really clear to understand what are the differences between ratios, rates, and probabilities. Ratios is pretty much when I compare two groups in a specific population. Let's say that I categorize people by a specific variable. They can be part of just one subgroup. If I compare the size of one group to the size of the other group, I have ratios. Rates describe the number of occurrence of an event for a given number of individuals who had the chance to experience that event per unit of time. Rates, I'm saying, let's say that I have a specific amount of women between 15 and 19 years of age. Women here, these women are exposed to the chance of having children. So we can count the number of births that they will have in the numerator. So rates, we are pretty much saying people in the denominator have a chance to contribute to the numerator. If I'm alive at the beginning of 2021, I can be in the denominator of a mortality rate because I have the chance of going to the numerator. If I'm alive now, I have the chance of dying in 2021. So that's a rate. I have the chance of moving from the denominator to the numerator. In the ratio, that's not possible. If I classify a population, let's say by men and women in a specific year, the group of men in that specific year cannot become women and vice versa. So I'm comparing to two different groups. I'm comparing the differences in sizes. The rates, I'm taking information for a specific time point, a specific population, and I'm seeing what's the chance of people in the denominator experiencing the event measured in the numerator. And that can be a fertility rate, having children, mortality, dying, or migrating. Someone who is at the beginning of the period, beginning of 2021, living in College Station, that person has a chance of moving out of college station. That person has a chance of moving to the numerator of an out migration rate from college station. And probabilities divides the number of events by the total number of people at risk in the relevant time frame. Probabilities, the easy way to understand probabilities and rates, that probabilities, we get the people who were exposed to a specific risk at the beginning of the period. It's going to be my denominator, and count the events, the numerator. Rates, we get population all over time. So if you're talking about rates related to 2021, I have to get population, different sizes of the population from January until December of 2021. Rates take into account time in the denominator. Probability doesn't. Probability gets the population in the denominator from the beginning of the period, okay? Example of ratios. Some really clear example of ratios that's really well known in demography. The sex ratio and the total dependency ratio. So ratios, they describe the relationship between two numbers, between two groups of people. Compare the size of one group to the size of another group. Compare the relative sizes of categories. So here I'm just giving different explanations to the same thing, ratios. Ratios indicate how many times the first number contains the second one. And in ratios, the denominator is not at risk of moving to the numerator. This term, being at risk of moving to the numerator, is pretty much saying that someone in the denominator has a chance of experiencing an event that will be counted in the numerator. In the ratios, that does not happen. Usually ratios are shown in percentage terms. So we divide the size of two groups, and then afterwards, we multiply by 100. The sex ratio, for example, we get the total population of males in a specific year, in a specific country, and divided by the population of females. In that specific year, in that specific questionnaire, people had the chance to choose a self-classifying either as male or female, so they cannot change. We are moving. We are comparing the two sizes, and we multiply by 100. The total dependency ratio in a specific year, in a specific country, I can either be from a child, a working age person, or an elderly person, depending on my age. 0 to 14, 15 to 64, 65 plus. People get older over time, but here we are talking about one specific time. I can be counted only as a child, working age person, or elderly person. And the total dependency ratio, we are just getting the number of children and the number of the elderly population in a specific country in a specific year, and divided by the working age population. It's pretty much showing me what's the percentage of dependence in that country. Dependence in the sense that children in the elderly population depends on the people of working age. Oh, but several countries we have child labor. Several countries people work when they are older than 64 years of age. Yeah, but here we have usually in demography these standards for these indicators, just to give an idea of this case here, the age composition of that population, and related to economic topic because we are talking about working age people. Right, so whenever we're talking about dependency ratio, we usually think about these three age groups, but we can see also total dependency ratio vary a little bit. The working age population can go from 15 to 69 or from 10 to 64. That can vary, but usually that's the standard that we will see, right? But here, the people who are in working age population in a specific year, in a specific population, they are not at risk of moving to the numerator. They are here And we are comparing that size to the size of children and the older people. So that's what our ratios. Okay? And this is one example of sex ratios from 1950 to 2015. For China in red, less developed regions in, what is that, light brown, and United States in blue, and more developed regions in green. And here we got the whole population in each one of these group of countries, or in these two countries, got the number of men divided by the number of women in each one of these years. So here, for the US, 1950, I got the number of men divided by the number of women, multiplied by 100. Back in 1950, the number of men and the number of women in the US was really similar. That's why we got 100 here, 100%. So this is the reference line here. Below 100, we have more women. Above 100, we have more men, right? Men divided by women multiplied by 100. What we see in more developed regions, in more developed countries, and in the US, you have more women than men. And then this differential has been declined, so it's getting closer to 100 again. In more developed regions, more women than men, but now we are getting to a society that we have more similar numbers of men and women in more developed regions. Why do we have more women than men in these countries? Overall, if countries, culturally speaking, don't have a preference for sons than daughters, you're going to have still more boys being born than girls. But throughout their lives, as we're going to see even in the next chapter, women live longer. Women living longer, when you compare the size of men divided by the size of women, is going to be below 1 unit. If you multiply by 100, it's going to be below 100. In less developed regions, or specifically in China, there are several factors going on there. In China, between 1979 until 2015, they had the one-child policy. That families, the government tried to impose that families should have no more than one child. A lot of them had more than one child, but it really had an effect on the chance of people having children. And also economic development in China. In the Chinese culture, people have more preference for boys. So women, when they were pregnant with daughters and they could see in the ultrasound, they performed an abortion until they got pregnant with a boy, and that influenced the sex ratio in the whole country. Because women, they prefer to have more boys. And actually, that's even before the one-child policy, you already had a high preference for boys in China. But not only that, in less developed countries, when families are poor and have less resources to give to the children, like food, and culturally they have a preference for their sons instead of their daughters, they will give more food, more resources to the sons. And then you increase mortality of daughters. And that overall creates these huge sex ratios. And in less developed regions, overall, you also have that. So it's not just because they have a preference for boys being born, so they perform an abortion when they are pregnant of daughters. It's also because in those countries, having limited resources, they usually use more resources toward their sons. Food when they are younger, education, and by giving more education, more food to boys than to girls, that it will impact mortality later on. Right? A simple graph, ratio, number of men divided by the number of women, but here we collected for several years for the different groups of countries. We can understand some of the culture, some of the economics in those countries, right? A really simple demographic measure. The total dependency ratio of India in green, China in blue, and the US in brown. That's the total dependency ratio. So we are getting children and older people divided by the working age population, by people between 15 and 64 years of age, and multiplied by 100. So in the US, for example, it increased the total dependency ratio in the 60s. Why that? We talk about this today. The baby boom cohort, right after World War II, you have an increase in infertility. More children, in this ratio here, more children increases the numerator, and then you set an increase in total dependency ratio. Fertility goes down, total dependency ratio starts to go down because this portion here of the formula starts to decline. And these people here start going to here as they get older. And then we have improvements in health in the country. So people live longer, have lower mortality. Lower mortality, what we expect for the next decades in projections for the next years, higher proportions of older people. So the total dependency ratio will start to increase again in the US. Not because of increase in fertility, not because of increasing the population of children, but because of an increase in the population of older people. Back in the 60s, the total dependency ratio went up because of increase in fertility here in the US. In the next decades, we expect an increase in total dependency ratio because people are getting older, living longer, lower mortality rates, right? That's what we are looking only with the brown curve here. India, in China, follows the same pattern. The total dependency ratio was actually higher back in the 60s and 70s compared to the US because fertility was even stronger. And after one-child policy and improvement in economic development, people start to have fewer children, total dependency ratio declines. Nowadays, in the next decades, we expect the Chinese people to live longer. It will have a higher proportion of people in older ages. Total dependency ratio starts to increase again. India is kind of like behind. If you look at the green line here for India, they had really high fertility as well, and then fertility is going down now. So total dependency ratio is declining, but it's still not, we do not expect in these next few decades to have a considerable amount of people in older ages in India because mortality, the improvements in mortality or in health, to better say it, are not as good in India as in the US and China. But if you look at this line here of India, it's kind of like the first half of China. It's kind of this beginning here for the US up to here. You increase and then you decline. China, the blue, you increase and then you decline. Same thing for India. So we should expect for the next decades after 2050, the green line to start to increase if we expect health improvements in India as well. Okay? Rates. For rates and probabilities, I got this information from this other article that's mentioned in the last slide, in the references here. And this article is more technical, so I try to just get the most important information for this class. Rates are an instantaneous measure that range from 0 to infinity. Rates describe the number of occurrences of an event for a given number of individuals per unit of time. So time matters in the denominator. Rates consider the time spent at risk. So what is the numerator? In the numerator, we measure the number of events that were experienced by people in the denominator in a specific time. And rates can be about all different sorts of things. But in demography here, the major examples are birth rates, death rates, and migration rates, the three components. The denominator in rates includes time. So for example, the sum of each individual's time at risk of experiencing an event for a specific population during a certain time period, that's the best measure to be included in the denominator of a rate. And it's called by demographers person years. Let's say that I want to know the mortality rate of a specific country. Let's say like now the US in 2021. I'm alive in January. I'm alive in February. I'm alive until the end of December in 2021. I would have contributed 12 months out of 12 in total to the chance of dying, but I did not die, let's say. The total number of person years that I will have, that I will appear in the denominator of this formula, is going to be equal to 1, because I lived 12 months out of 12. Let's say that I die at the end of June of this year. So I would have lived from January until the end of June. I lived 6 months out of 12. So I will count in this denominator as 0.5, 6 out of 12. In the first example that I lived from January until the end of December, I count 1 in the denominator and 0 in the numerator for mortality, because I did not die. If I was alive in January and I died at the end of June, I will count 0.5 in the denominator, 6 months out of 12 I was alive, and I will count the numerator as 1 death. First example, I count as 1 in the denominator, 0 numerator, because I was alive, I did not die. Second example, I was alive for only 0.5 portion of the time, so 0.5, denominator, numerator I count as 1. It's already really difficult to collect information about population size and deaths and births in migration for one single time in a specific year. It's hard to do that. How would I calculate the population size of this specific country in every single month? It would be too complicated. So one way to use an approximation of the denominator of the rates instead of using the person years, what I can get is the population, the mid of the period, July 1st, with the assumption that people are dying and being born in the same rate before and after July 1st. Or if I have the population in January 1st and December 31st. So I can get the average of these two populations with the assumption that people were dying, being born in the same rate, right? So rates, the best information for the denominator is person years. It's hard to collect that information, so refine. So I get the population in the mid of the period or the average of the population at the beginning and the end as approximation for the denominator. Examples, the crude birth rate and the crude death rate. And in these examples here, the total population is the population in the mid of the period. This is the example of the crude birth rate in the US. Declined a lot until the 70s. It has been more stable and expected to be stable also for the next decades. And the crude death rates also stable over time. And in this case here, the people being counted in the denominator have a chance of having children and have a chance of dying. That's why it's a rate. And probabilities does not include time in the denominator. It divides the number of events by the total number of people at risk in a relevant time frame. To better understand it, I said an approximation for the denominator of rate is the population the mid of the period or the average of the population beginning and the end. For probability, an approximation, is the population at the beginning of the period. I don't care about time. How was the population at the beginning? That's the denominator of a rate, probability. Time matters for rate. So I can get an approximation, population in the middle, average of beginning and end. Probability, just the beginning. Cool? So I took 3 classes to finish chapter 1. Awesome, good. I prefer to go slower, so try to better explain things. Right now, quiz 1 is available on Canvas, and it's going to be available until tomorrow, Wednesday, until 12 p.m. When you answer the quiz, only 2 questions, 0.5 points each question. You will see if you got it correct or wrong, but if you got it wrong, the correct answer will appear to you only tomorrow by 1 p.m. That's the standard that we're going to have here, okay? Open from now until tomorrow, 12 p.m. See the correct answers at 1 p.m. Once you start the quiz, you have 5 minutes to answer the 2 questions. These questions, they come from a question bank, and most of these questions were actually created by the publisher of the textbook. And Canvas select 2 questions randomly. So the questions will be different for each one of the students. Okay? Thank you very much, and I see you guys on Thursday. Thank you.